Good morning, everybody. Welcome to Maths for Week 6. This is Lesson 1 for Monday, Year 6. Today, we are looking at function patterns. Now, I've actually looked at these in the past, but I thought it might be a good idea to revisit it, particularly given that some people were getting confused with function patterns and this other type of pattern, which is called a recursive pattern. So today, what you're going to be doing is you're going to be continuing and describing a function pattern. So continuing the sequence and also describing how the function pattern works. To do that, you need to understand the difference between a recursive pattern, which I mentioned before, and a function pattern. Also, you need to identify a relationship between the position and the term of a function pattern. Now, you can see here all these pink words that are bolded in pink. That's all different vocabulary which we're going to be using today, and I'll go through all of these. So if you're a little bit confused, you're like, what's a term? What's a recursive pattern? We're going to look at that in a minute. You'll also write a rule for that relationship using words, and you'll also complete what's called a table of values according to a rule. So it's quite a lot to get through today. We have looked at this in the past before, but I'd like to kind of revisit it because it's really important, particularly going into high school and you're moving into the kind of field of algebra. It's really important to get a good grounded knowledge in this kind of foundational skills of identifying patterns and knowing how they work and describing the rules for them. So let's have a look at recursive patterns and function patterns. So I mentioned before these recursive patterns, which I'm going to put a number 1 here. And this is a sort of pattern you would have seen from kindergarten all the way up until year 4, where you're finding the difference between these numbers in the pattern. So here I can see I've got 4 and 8. So there is a difference of 4. And then 8 and 12, difference of 4. And here the rule we could say is increasing by 4. So all I'm looking at is these numbers or these terms in a pattern. So a term is either the number or the shape or whatever appears in the sequence of the pattern. So these numbers here are terms, kind of like a school term, but a different use of this word. And I'm just looking at the difference between them. So I can say here it's increasing or getting bigger by 4. And see how I've used words here as well. I haven't just done plus 4. I've used words to describe the rule. So I'm saying increasing by 4. This is a kind of basic, simple pattern which you're kind of first introduced to. What I'd like you to move on to now is thinking about this function patterns. So here we've got 2 different rows and we have columns as well. And the rows are actually labeled. So the first one here is the position in the pattern and the second one is the value of the term. So position in the pattern, number 1, this is the first number that's going to appear in the pattern. Second number, and so on. So let's look at this again. So I've got 4, 8, 12. Well, there's a difference here between plus 4, plus 4. But unlike the recursive pattern above, what I'm looking at is I'm not looking at the relationship between these 2 numbers that are horizontal, so the 4 and the 8. Rather, I'm looking at what's the relationship between the position 1 and 4. What's the relationship between 2 and 8, 3 and 12? And I can see here, well, 1 times 4 is 4, 2 times 4 is 8, and so on. So I can say, well, do you know, a rule for this pattern could be to multiply the position of the term, multiply the position in the pattern, I should say, by 4. And the reason why we're moving away from this recursive pattern, not to say that they don't exist and they're patterns within their own right, is that this is an additive process. So it means you're just adding on. You're just going, okay, well, the next number here is going to be 24 because I just need to add 4. Next number is going to be 28. Whereas the function pattern down here is actually multiplicative. That means that we're using multiplication to help us figure out what the value of the term is going to be. And the reason why this is probably a more powerful or useful pattern is that you can actually use it to find out any term in the pattern, any position. So here, what is the 70th term? I don't need to keep on adding plus 4, plus 4, plus 4 all the way up to the 70th position. All I need to do is multiply 70 by 4, and I get my value, or the term in the pattern, which here is 240. So it's actually a much more powerful, much more useful way of thinking about patterns. And it's a kind of relational thinking where you're thinking about what's the relationship between the position and the term. So that's a nice simple one involving one operation. Let's look at another type of pattern involving more than one operation. So we know, remember from a few weeks ago, we looked at operations as plus, minus, multiplication, and division. Now up the top here, we've got our recursive pattern. So it actually starts at 3, and then it goes to 5, 7, and 9. So a way I could describe this pattern is say, well, start from 1 and increase by 2. So 1 is the first number here, plus 2 gives me 3, and then I plus 2, and so on. Yeah. Now, if I want to find the 70th term here, or the 151st term, it's actually going to be quite tedious trying to figure out that process. A better way of thinking about it is to go, okay, let's put it into a function pattern here. So what's the position in the pattern? So the 3 is position number 1. And what's the relationship between the position and the value? So here I can go, well, I have to think about it a little bit carefully. 1 times 3, oh, okay, that's 3. Let me check that for position 2. 2 times 3, well, that's not going to work because I've got 5 there. So I'm going to have to think about a different rule. So here I'm going to say, well, 1 times 2 is 2, plus 1 is 3. Because I know that 3 is 1 greater than 2. Let's try this one here. 2 times 2 is 4, plus 1 is 5. Okay, so this pattern works. So the rule for this pattern would be multiply the position, which is this top row, by 2 and add 1. And I can see that continues all the way here. 3 times 2 is 6, plus 1 is 7. 4 times 2 is 8, plus 1 is 9. So for my 70th position, it's 70 times 2 plus 1. So with these function patterns, it can be a single operation like multiplication or division, or even just plussing or minusing, but they can also have more than one operation. So it can be, divide by 4 plus 6, or multiply by 2, add 1 here. And I've described it again using words. So I'm describing the rule using words. So we've looked at function patterns as looking at the relationship between the position of a term in a pattern and the term itself, and then applying a rule to that. But I also want to extend upon that idea of what a function pattern is, because it's not just that. Another way of thinking about it is an input where a rule is applied to that input. So this is what you are putting into the system or into the machine. This is the rule that it's applying, and this is the output. This is what you end up, the number you end up with. So here, for example, I've got 8. I'm going to put 8 into this pattern. I'm going to multiply by 2 and subtract 2. That's my rule, and it's going to give me 14. And I can put this idea of input and output into a table similar to the position and value of the term table on the previous slide. Here I've got my input is 4. So if I multiply by 2 and subtract 2, my output is going to be 6. Similarly here with 37, my input is 37. I apply my rule, multiplied by 2, so that's going to be 74, and subtract 2 is 72. So it's not kind of bound by this idea of position and value of the term. It's really just about input and output. I could put anything here, to be honest. We'll look at that tomorrow in tomorrow's lesson, but I kind of want to extend upon that idea of just thinking that, oh, okay, this is all about filling in a table, because it's not. It's looking at the relationship between two numbers, the relationship between this input number and the output number, or the position number and the value of the term. So here, this is a different way of presenting numbers within a pattern. Instead of having it horizontally, I've just displayed them vertically like this. Let me just grab my marker. Yeah, and it's not in the table, but it's thinking about what's the relationship between this input number, which is 27, and this output number, which is 9. So 27 and 9, 15 and 5, and 3 and 1. So they're all going to have the same rule applied to them, these input numbers, to get the output number. Now, I know there's a relationship between 27 and 9 because I know that 9 times 3 is 27. I also know that 5 times 3 is 15, so I'm just going to write this here. 5 times 3, 9 times 3. Oh, and 3 and 1, well, there's a relationship, 1 times 3. Yeah. But because my input number here is 29, it's going to be the inverse operation. So it's going to be the opposite. So my rule, same with 15 and 3, is going to be divide the input by 3, and that will give me my output. So for example, if my input number was 1, my output would be 1/3. Or if my input number was 30, my output number would be 10. Okay, so here I've got my input numbers, and my output numbers in this pattern are 44, 14, and 68. And so all these numbers on the left here have had a rule applied to them, the same rule, to get their output counterpart. Now immediately I can't see a relationship between 7 and 44, but I can see a relationship between 2 and 14 because I know that 2 times 7 is 14. 11 times 7 is not going to give me 68, so that times 7 rule is not going to work. Same here for 7. 7 times 7 is 49, so that's not going to work. But I'm going to see if I can find something that's kind of close, because this might be a two-step problem. So it's not going to simply be multiplied by a number. It's going to probably be a two-step problem. So here, 7 times 6 will give me 42. And if I add 2 more, it's going to give me 44. So 42 plus 2 is 44. Here, 2 times 6 is 12, plus 2 more is going to give me 14. 11 times 6 is 66, plus 2 more. Oh, that's the worst plus sign. Sorry about that. Plus 2 is 68. So here, this rule, or this process here, times 2 plus 6, or multiplied the input by 6 and add 2, is going to give me my output. So that's the rule there. So this is a two-step pattern. I'm looking at the relationship between the input and the output, and I'm trying to find a rule that will work to describe that relationship between all of these numbers here, all these input numbers and all of these output numbers. The kind of one-on-one relationship, I should say. So far we've looked at function patterns and the difference with recursive patterns. And with function patterns, we're looking at the relationship between two numbers. Rather than the difference between two numbers in the pattern, we're looking at either the position and one of the terms in the pattern, or this idea of what's the number we input and the relationship between that and then the output number. Now, this idea of input and output may seem rather abstract, but we actually use it in real life every day, particularly if you're going to the supermarket and you're buying fruit and veg, and the cost of that fruit and veg is calculated based on its weight or its mass. So here, I'm going to apply that input rule output model to bananas. So here our input is the mass in kilograms, and the rule that's applied is the input multiplied by $1.40 will give me the output, which is the total cost, which is how much I need to pay. So here I put $5 or 5 kilograms, I should say, of bananas. That's my input. My rule is 5 times $1.40, because I put my input in here and multiplied it by $1.40, and my output here is $7. That's the total cost. So this actually gives me a standard rate. So for example, if I were to put 10 kilograms in here, then my total cost would be $14 and so on. So it gives me a consistent, a fixed rate each time, which is another way of thinking about a pattern. And we use this for a lot of different things, for the cost of electricity and gas or energy, petrol, fruit and veg, as I mentioned, a fixed rate home loan. There's lots of other situations where we use this idea of a rate, which is just another way of basically applying this a pattern rule, or a kind of input-output model, a function pattern. So lastly, let's look at another example here, and this is the rate that a DJ charges for their services. So Robo DJ charges $70 an hour, as well as a $100 appearance fee. So the $100 appearance fee is a one-off cost, and then everything else is charged by the hour. So to describe this using a rule, I could write hours, which is my input, multiplied by 70 plus 100 equals the cost. So let's apply that now to these different situations. How much will she earn if she's booked for a weekend-long festival, which goes for 48 hours? Well, firstly, I need to input my 48 hours in here, multiply that by 70, which gives me 3,360. Then I add $100 onto that. It gives me $3,460. That's my total cost. Now I split this over 2 lines. You could have it all in the 1 line. I like to show that it's a 2-step pattern. So I split it over 2 lines, and I try to, not a great example here, keep these equal signs in line with one another. Here, B, a child's birthday party is 3 hours. So I'm going to input my hours here into the hours section, multiplied by 70, which gives me 210, plus $100 gives me 310. So both of these events are charged at the same rate using the same rule. So this is another way of thinking about a pattern. Okay, so some of the main ideas from today. The first one, which is the one I want everybody to really focus on, is this idea of a function pattern, how it differs to a recursive pattern. So a function pattern involves looking for the relationship between 2 or more varying values. So that could be the position. So here, position number 1 and the term in the pattern. So position number 1 and our term is 3. Position number 2 and our term is 6. Position number 3 and our term is 9. We're looking at what the relationship is between these 2 varying values. Yeah, so these values can change, and as they change, we need to figure out what the relationship is. This is different to a recursive pattern, which is really just additive. So recursive pattern, you'd just be looking at, well, 3 plus 3 is 6. 6 plus 9 is 3. So 6 plus 9, 6 plus 3 is 9. Going a little crazy. With a recursive pattern, you're just looking at the difference between each of the terms in the pattern. So it's much simpler. Where here you're looking at the relationship between these 2 or more values. So the position and the term, or the input and the output. It could be something else, but today that's just the 2 we've looked at. This relationship can be described by a rule. And a rule can involve a single operation, for example, multiply by 4, or more than one operation, times 2 plus 3, for example. Function patterns are really effective in that they allow us to determine the value of any position in the pattern, or any input in the pattern. So for example, the 129th number in the pattern, or if I was to input 129, what would my output be? And they are used to describe fixed rates. So for example, we looked at bananas, how much you pay for 5 kilograms of bananas. You're going to be paying the same proportionate rate if you get 100 kilograms of bananas, or 39 kilograms of bananas. You're still having the same rule applied to it. Similarly, with that last example with the robot DJ, you'll have a similar example in your problems today, where you're applying a rate to an input to find out what the output is. Okay, thank you very much for your attention today, guys. Good luck with it. I'll kind of unpack this idea of function patterns a little bit more tomorrow and kind of explain to you why we spend so long on them and why I think, and a lot of other people do, think they're so important, particularly as they're going on into more complicated maths in high school and so on. All right, see you tomorrow. Hi everybody, welcome back to Year 6 Maths for Week 6. This is Lesson 2. Today we are continuing looking at function patterns. So today you're going to be continuing and describing function patterns, similar to yesterday, but there's a focus on using inverse operations to identify an unknown position or an input. So we looked at function patterns as having these two varying values. The first one could be a position, and the second one could be, let's say it right, term, because a term is whatever appears in the pattern. And let's say the position here is just 1 and the term is 4. And then somewhere further along, we don't actually know what the position is, but we have the term for it. So today we're going to be trying to figure out what the position is, or the input is, because this could also be input, using an inverse operation. So inverse operations are opposite of one another. So addition and subtraction. Addition is getting larger, subtraction is getting smaller. They are inverse to one another. Same with multiplication and division. Multiplication is getting larger by groups of, and this is getting smaller or breaking it, kind of undoing the multiplication. So they're inverse to one another. So very useful, powerful mathematical knowledge there of knowing these inverse operations. And we can use those to identify or find unknown information in our pattern. Secondly is understanding that the input and output can be substituted with other labels, or the position and the term can be substituted with other labels, so you can call them other things. Write a rule for the relationship or the using words, and write an equation which describes a rule. Now technically this is not really Year 6 content, but considering we've looked at this in the past and we've used words quite a lot to describe rules, I thought we might introduce you to this idea of using an equation to describe a rule. So yesterday we were looking at function patterns as a relationship between two varying values. That could be the input and the output, or the position and a term in that pattern. So we had our thing here, first position, we wanted to say 5, second position was 10, third position was 15. And we could figure out by looking at the relationship between these two values, the position and the term, that this rule was multiply the position by 5, and that will give you the term in the pattern. So we're trying to figure out what the rule was yesterday. Today, we're going to have a situation where we're going to have might have the output, and we might have knowledge of the rule. So we might have a situation where we've got 1 and 5, 2 and 10, 3 and 15. But now we've got an output here where our output is 30, but we don't know what position it is. So what's the position here for this particular term in the pattern? Now, instead of applying the rule where we multiply it by 5, because that's not going to work, because for this rule to work, we need to multiply the position by 5. We don't have the position. So we can apply the inverse operation. That's the opposite operation of multiplication, which is division. So in this case, we would do 30, which is our output or our term, divided by 5, and it's going to give us the position or the input, which is 6. So it's really just a case of reversing that rule, and that will give us that value there, or that position or the input. So yesterday we had the example of the comics, and this was the way of calculating the total cost of the comics was applying this particular rule, and it followed a pattern. So here the input was number of comics multiplied by 7 will give you the cost of the comics, and then you add the flat fee of $1.50, and that will give you the output, which is the total cost. But if we had a situation where we had, someone paid this much for their comics, they paid $36.50. We can just backtrack to find out, well, how many comics did that person actually buy? So I just reverse the rule here. So I do the inverse operation of addition. So I subtract the $1.50, which will give me $35. 35. Then I divide that by 7. Now my answer is not going to be in dollars because I'm talking about comics. So my answer is going to be 5 because 35 divided by 7 is 5. So that person bought 5 comics. So I can again use that inverse operation to find out the unknown input there, which is the number of comics. Okay, so here we have our values table. And when I'm talking about values, I'm really just talking about numbers. But there are 2 types of values here. We've got hours and we've got liters. So everything in this top row, those values are hours, and the second row, those values or numbers are liters. So they are different to one another, but they are numbers. Now what I want to do is find the rule or the relationship between these 2 sets of values, hours and liters. So here I've got 3 and 30, and the relationship there, well, I know that 3 times 10 is 30. Now that might not be the rule for the rest of the pattern. I do have to check. In the second column, I've got the hours, but I'm missing the liters. So I kind of need to continue going right. Here I've got 15 and 150. Well, I know that 15 times 10 is 150. And those are the only 2 columns where I have both sets of values. I've got the hours and the liters. So for all intents and purposes, I'm going to say that the rule, which I'm going to write down in this bit here, is going to be hours multiplied by 10 is the same as liters, or give me liters. Yep, that's the rule there. So here, 3 times 10 is 30, and liters is 30, so they're the same, they're balanced. It's a balanced equation. Now, what I want to do is figure out what the rest of these values are. So here, 6 times 10 is 60. But I'm here at 200. Now I can't just times 200 by 10. That's not going to give me my the hours, because that's the multiplying by 10 is how I get liters. So I want to do the inverse operation, and I'm going to divide by 10, which will give me 20. So I can even write a rule here. I could say, well, the liters divided by 10 is the same as hours. Yep, so 200 divided by 10 is 20, 20 and 20, they're balanced, so they're the same. And remember that equal sign is the same as, so important. Here, 35 times 10 is 350. This situation, again, I'm going to have to do the inverse operation, so I'm going to divide by 10 because I want to find out hours, and I know that liters divided by 10, which is the inverse, gives me hours, so that's 170. Now at the end, I've got this really interesting situation where I've put a square. Now we know a square is not a number, But particularly as you move into algebra, as you go into high school, you get situations where you kind of get either letters or numbers or symbols that are substituted for an actual number. So here, even though I don't know what this number could be, it could be anything. When I'm writing it down here, well, I know the rule is hours multiplied by 10 gives me liters. So all I have to do is put the symbol or the letter or whatever it is and apply the rule. And there you go. That's what the value is. It's the square, whatever number that's going to be, because we don't know the number yet, multiplied by 10. It's that simple. So here I have my table of values organized slightly differently. So you might have seen situations, let's go with our hours and liters, and they're displayed on different rows. So they're kind of displayed horizontally, whereas here they're displayed vertically. And my values actually just have A and B. So it doesn't really matter, what we're dealing with as such, as long as we've got labels for these values. They could be different things. They could, one could be hours, one could be liters, one could be kilograms, one could be dollars. Doesn't really matter here. What I need to know though is these are my A values. So 5 and 20, and these are my B values, all the ones in this column here. Now before we start describing or writing this rule, I'm going to find out what the relationship is between these two values. That will give me my rule. So here, 5 and 35. Well, I know that 5 times 7 is 35. Now I'm missing a value here and I'm missing a value here, so that's not really going to help. But here I've got both values, so I'm going to look for that relationship again. Remember, with function patterns, we're always looking for a relationship between these two values. 20 times 7 is 140. So my rule is multiplied A by 7 will give me B. But I want to find out what these missing values are here, so I just need to do the inverse or the opposite. I know the inverse of multiplication is division. So 77 divided by 7, now we're going this way, is going to give me 11. 84 divided by 7 is going to give me 12. So now I've filled in my table of values. What I want to do is I want to think about writing this as a rule. Now we could write it with words. So example, multiply, this is the worst handwriting ever, multiply A by 7. But what I'm going to think about is using an equation, which is a type of number sentence, to express this pattern or this rule. So A multiplied or times by 7 is the same as B. Now I've used an equation. Now equation is a type of number sentence where it has an equals sign in it, and both sides of these balance. So here I can see that my A value is 5, so 5 times 7, that will give me 35. And I've got 35 on this side, so now they're balanced. So that's what an equation is. It's just a number sentence where you've got an equal sign and both sides balance. Now this looks suspiciously like algebra, which is something you'll look at more in high school. But what we actually have here, instead of writing 5 and 35 here, I've actually substituted the value in here. So here I've got the A value and the B value. So this means that whenever I see this, whenever I have an A value, all I need to do is multiply it by 7 and it'll give me the B value. So let's say it's my A value, I could just substitute, I could say my A value is 10 times 7 is 70. So this is how patterns relate to algebra. It's one of the ways they relate to algebra. but particularly function patterns. It's a consistent rule that can be applied to any set of, or to those specific values, and you can just slot in the values in the position of these, the A and the B, which are kind of substituted in. I'm not going to spend too much time on that today, but there is a activity where you'll see this. So don't freak out because there are letters. Basically, just recognize that these are values here, and they might even be unknown values. So for example, if I had, class X, no, maybe not X, X is not a great one, Y. So here, if I wanted to find out what the B value of Y is, it's going to be Y, follow my rule, times 7. Yep, that would be my B value. Or for those people who know a little bit of algebra, it is 7Y. Yep, that's simple. Now on this last example, I have my values table with my two columns A and B. So I've got my A values in this column and my B values in this column, and it's filled in. So we're not trying to find missing values for this one. The first thing I want to do is find out what my rule is. And to do that, I need to look at the relationship between the A value and the B value, and this A value and this B value, and so on. That will give me the relationship, which is the rule, which I can apply to any A value that I decide to slot in. You can also, on the inverse, if I don't know what the A value is, but I've got the B value, then I can apply the inverse function. So here, this is a little bit trickier because it actually involves more than one operation. So I know that I can't multiply 4 by something to get 21. Now, it actually might be a decimal number, perhaps, or some kind of fraction, but I'm just going to deal with whole numbers for today. So what we're going to do is I'm going to say, well, I know that 4 plus 3 is 7, and 7 times 3 is 21. Same here, 6 plus 3 is 9, 9 times 3 is 27. 7 plus 3 is 10, 10 times 3 is 30. So this rule applies to each of these situations. Again, 8 plus 3, ahead of myself, is 11. 11 times 3 is 33. So to write that as a rule, I could use words, but in this situation, I've decided to use an equation. Remembering an equation is a number sentence, which uses an equal sign, and both sides are balanced. So here I've decided to say, well, the rule is A plus 3. And I've used my grouping symbols, which we looked at the other week, to say, do this bit first. Anything in the grouping symbols, you always do first. So I do my A plus 3, then I multiply that by 3, and that will give me my B value. So let's say we put the A value in here. So let's try it with 4. So 4 plus 3 is 7. 3 times 7 equals 21. 21 is equal to 21, so that is true. So both sides are balanced. Now this is kind of an early introduction to algebra, again showing you that relationship between function patterns and algebraic expressions. Okay, here are the main ideas from today. So you'll notice actually this first dot point is the same as yesterday. This is the main idea that I'd like everybody to take away from this week. It's the difference between a recursive pattern where it's additive. So we've got a pattern here, let's say it's 1, 4, 7, 10. And the rule is start from 1 and add 3 each time. So it's basically plus 3, plus 3, plus 3, and so on. So that's additive. We're just adding. And moving to this idea of a function pattern where we're looking at for the relationship between 2, or in some cases more, values. So we've got our values. They could be a position and a term. And let's say we put them in this kind of horizontal array. It doesn't have to be in that particular arrangement. That's the table. And we've got our position is, let's say it's 3, and our term is 9. Position 4 is 4, and it's 12. Well, I can see the relationship there. This is the relational thinking. Well, 3 times 3 is 9, 4 times 3 is 12. So my rule is position times 3, or multiply the position by 3 to get the term. That's the main thing you need to take away from this week. Secondly, the main thing from today is that where we've got an unknown value, for example, we've got the output value, so I might have the term here, so I might have, let's say I've got 33, and I know the rule is multiply a position by 3, I have to do the inverse to find out what the position is, the opposite. So instead of multiplying by 3, I'm going to divide by 3. So my position would be 11. So we can use inverse operations to find an unknown input value. The next thing, which is not so important, but you would have seen this week that I've been kind of chopping and changing some of the labels for the values. So we had kilograms and hours, position and term, input and output, A and B. The values can be labeled anything. Essentially, it doesn't change how the pattern works or how it's the rule that's applied. It just sort of changes how we describe it. Really, that's all it is. But knowing that I've got my A values, for example, and my B values, I'm trying to find that relationship between the two of them. Or my kilograms and my hours, trying to find that relationship between the two of them. That makes a smiley face. Okay, second last thing is we can write the function rule with words. And if you can just do it with words, that's absolutely fine. But we can also take it to the next level and express it as an equation. So an equation is a number sentence which has an equal sign in it, and both sides are balanced. They are equal, they're equivalent. That's why it's called an equation. So for example, it could be nice and simple, like A times 7 gives me my B value, so A times 7 equals B, or it could be multi-step, 3 times brackets A plus 3, so I'd do that first, equals B. And lastly, this idea that function patterns and functional thinking is closely related to algebra. So in algebra, you're often trying to find out what's the relationship between different values. So these kind of skills of thinking about, and trying to identify the relationships are really foundational to algebraic thinking. And also this idea of, instead of using words, expressing it as an equation. Again, that's also strongly related to algebraic thinking, which is particularly important in high school maths. Okay, thank you for sticking with me. I hope you're enjoying this. It's a little bit more challenging than the first time we looked at function patterns, but I thought I'd kind of take it to the next level since we're revising it and kind of add a little bit extra on to those people who are kind of comfortable with finding the relationship, but they kind of want to take it to the next level. All right, I'll see you for lesson 3 tomorrow. Welcome to lesson 3 for week 6, year 6 maths. Today we are looking at something slightly different, but still on topic, and that is generalizations. So today we're learning to make generalizations about numbers and number relationships. That's interesting, we've got this one here, number relationships, considering we've been looking at function patterns and how that's a relationship between two values or two numbers and finding that rule. Now, our success criteria today are recognizing numbers and number relationships that can be generalized, writing the generalization, and checking that your generalization is true. And if it's not true, if it's false, you might need to refine it to make sure that it is true. So generalizing or generalizations, what are they? Well, it's looking for underlying patterns or common properties in mathematics. So let's take even numbers, for example. An even number of objects can always be split into two equal groups. That's an underlying pattern when it comes to even numbers. So we've got, let's make 6, and I can always make 2 equal groups of 3, or 10, 2 equal groups of 5, and so on. It's a property or a pattern that can always be applied. So the generalization itself is either a principle or I like a statement the best. It's saying something about them, about this pattern. It's a statement or an idea that can be generally applied, that it's always true. And it's a core part of our mathematical thinking. That means it's a really important part. It underpins a lot of the mathematical laws that we take for granted a lot. But it's good to be thinking about it critically and to be able to understand how those laws apply. But also being able to generalize more broadly and being able to make these kind of statements about even numbers means we're not focusing on those simple patterns. We can actually notice more complex patterns, or it kind of frees up our brain power to be thinking about other things rather than just being like, well, can I split 8 into 2 equal groups? I don't know, can I? Well, I know 8's an even number. There you go, done. Yep, makes it a lot simpler, a lot quicker. So here's our first generalization, and it's a nice simple one. Adding an odd number to an even number always results in an odd number. So up here in the blue section, I've tested it out with a diagram. So here I've got 1 plus 2 equals 3. I know that 3 is an odd number, so that's correct. 3 plus 4 equals 7. 7's an odd number, that's correct, and so on. 5 plus 6 equals 11. Yep. So here, this is a nice, explicit, unambiguous statement. Nobody can really misinterpret this generalization. Adding an odd number to an even number always results in an odd number. So I'm going to say that generalization is true. Now, knowing what I know about the inverse relationship between addition and subtraction, I can actually get another generalization from this, and that could be that subtracting an odd number from an even number always results in an odd number. So let's say we've got 4 minus 3 equals 1, or 6 minus 5 equals 1. Likewise, I could say subtracting an even number from an odd number always results in an odd number. 3 minus 4 equals -1. 5 minus 6 also equals -1. There you go. All those numbers are nice and closely related. Now, there's actually more generalizations I could make about these number sentences and other numbers, but that's just an underlying pattern or property of our number system, of our mathematical number system. Time to generalize again. So here I've got some number sentences or equations, and they all involve multiplication. So 5 times 5 is 25, 12 times 4 is 48, and 9 times 9 is 81. And I'm going to make this generalization. I notice that the product is always larger than the starting number. So I'm going to say multiplying a number by another number results in a larger number. Seems fair enough. I know that multiplication is like repeated addition. This 5 times 5 is like 5 plus 5 plus 5 plus 5 plus 5, or like 5 squared. So 5 multiplied by itself, or 2 5s multiplied, I should say. But what happens when we try to multiply this first number by a decimal number or a fraction? Now, these are both numbers. They're not whole numbers, but we know that 0.5 is a decimal number. We can plot it on a number line. And same with fractions as well. So a fraction is a proportion or a ratio, or a self-contained division problem, but it's also a number. We know that we can plot half on a number line between 0 and 1, and it's halfway between those two numbers. So I'm going to revise this generalization. I'm going to say, well, multiplying a whole number by another whole number results in a larger number. Oh, that's all fixed. But what about 0 and 1, if they're my factors? Well, 0 I'd say it's actually a whole number, which sounds a little bit strange, but we consider it a whole number. Same with 1. So here, when I multiply 4 by 0, my answer is 0. So I'm not getting a larger product, I'm getting a smaller product of 0. And here, my product is the same as my starting number. It doesn't change. And this gets even trickier when I consider, well, what about my negative integers? Now, you can say negative numbers. I haven't really specified here what, number is such a broad term. So here, -3 multiplied by 2 gives me -6. So we know 0 is here, -3 is here, and -6 is here. So it's actually less than -3. So -6 is less than -3. Same here, next started with -2 and multiplied it by 5, or 5 by -2, and we've ended up at -10. So sorry, we started here, we ended up all the way down here. So that this rule here of multiplying a number by another number results in a larger number, it's not true, because there's all these exceptions to it. So we need to be very specific about how we would phrase this and how it would work in practice. Now, I'm not too sure. You couldn't say multiplying a whole number, just this one we've got here, multiplying a whole number by another whole number, because these ones here, I'm going to use a different color. These guys here. And also, these are whole numbers over here. Even though they're negative numbers, they're whole numbers. So we could say multiplying a positive number by another positive whole number results in a larger number, where that number is not 0 or 1. So it's quite a long generalization, but whatever generalization we make, it needs to be true, and we need to really kind of think about those situations where there might be exceptions. And it's like, well, is it really a generalization? It's too general. It kind of needs to be watertight. Now let's look at a pattern here. So we've got our square numbers. We've got 1, 4, 9, and 16. So hopefully you'll recognize that. And we know with our square numbers, we can represent them as the number itself and to the power of 2, which basically means the number multiplied by itself, or the number 2 ones multiplied, or 2 2's multiplied for 2 to the power of 2, and so on. So one generalization we can make about square numbers, and this is how we get their name, is that a square number can be arranged into an array with equal rows and columns. So there's always the same number of dots in each row and column if we arrange it that way. So that's one generalization we can make. But let's look at the pattern and how it grows. There's actually more than one generalization we can make about square numbers. So here we've got a diagram which shows how the pattern is growing. So we start off with 1, and then we add 3 to it. Then we go from our next square number, so from 2 to the power of 2, we have 4, and then we add 1, 2, 3, 4, 5. Here we have 9, and we add 1, 2, 3, 4, 5, 6, 7, and so on. So there's a few different generalizations you can make about this. But one that I came up with, looking at it slightly differently, was 1 itself is a square. 1 plus 3, so 1 plus 3 gives us 4, which is our second square number there. 1 plus 3 plus 5 gives us 9, which is 3 squared. Again, 1, 3 plus 5 plus 7 gives us 16. So another generalization I could make about this particular square number pattern is that each positive square number, except 1, is the sum of 2 or more odd numbers. So here we've got 1 plus 3, 1 plus 3 plus 5, and so on. So that's another generalization you can make about that pattern. So it's seeing beyond, well, what is a square number and how do we define a square number, which is kind of more about this, and actually looking at the patterns with square numbers, looking at the properties of square numbers and what generalization, what general statement or statements can we make about this pattern about square numbers. Now, the last thing I'm going to talk about today is generalizing about operations. Now, we had that example before with multiplication, and we realized that generalization that when you multiply a number, it always results in a large number wasn't actually true, and it needed to be refined. I'm just going to talk about a few basic generalizations or properties that you're probably already aware of, and you're going to today have a few number sentences where those might apply. So here we have 3 plus 6 plus 4 equals 13. And I know that with addition number sentences, they're governed by this commutative property, which means that it doesn't matter which order I add these addends in, that's the numbers that I'm adding together, I'll still get the same sum, which is 13. So I can have 6 plus 4 plus 3 equals 13, 4 plus 6 plus 3 equals 13, 4 plus 3 plus 6 equals 13. Now, this is quite useful, particularly for mental addition, where you're like, well, I know 6 and 4 are friends of 10, and I know it's easy to add a number to 10, so 10 plus 3 is 13. It's also useful in a whole lot of other applications, but that's just one example of how knowing, being able to generalize or about operations or understanding the different properties of these operations can help us. Now, that's a very basic example. Here, a little bit more complex, we've got inverse operations. So we know that addition and subtraction are inverse operations, they're the opposite of one another. So 6 plus 7 equals 13, so I can say that 13 minus 7 equals 6. Down here, I've got a value where I don't actually know what it is. It's been replaced with a triangle, so it's an unknown value at this stage. So here I can say a triangle plus 7 equals 13. So I know with inverse operations, 13 minus 7 equals triangle, and I know I can perform that operation, so I know that the answer will be 6. And this last one here, we don't actually have the values. We've got a triangle and we've got square. So triangle plus square equals 13. So 13 minus square equals triangle. Now, it's not about finding out, is this a 4 and is this a 9, or what is actually the value of these. It's more about simplifying the equation or thinking about it in another way, thinking about the relationship between all of these values and also the operation as well. So that's going towards more algebraic thinking, where it's about representing or simplifying a mathematical problem or looking for the relationship between the values rather than just finding the answer. So that's more arithmetic. And when you move into algebra further on in your mathematical learning, it's more about representing and finding relationships. That's why this week has all been focused about function patterns and relationships. It's such an important way of thinking in mathematics and mathematical thinking. Now, I did say that was the last slide, and I forgot I had another slide. So here we're talking about writing a generalization. We've got two number sentences at the top. 23 plus 0 equals 23. 0 plus 23 equals 23. Now, you could say that's the commutative property of addition there. But here we've got another generalization. So all of these generalizations down here, they're all talking about adding 0. And what I want you to think about is which one of these is probably the most effective generalization. It's the clearest and it makes the most sense. So let's look at these first two. Adding 0 leaves it alone. Adding 0, it stays the same. So that makes sense in a conversational sense. Adding 0 to 23 leaves it alone, it still stays 23. And adding 0, it stays the same. Again, it's very conversational. But this idea of leaves it alone and it stays the same It's not really mathematical language, and it's also a little bit confusing. So we know adding and zero are mathematical terms, but it's the idea of leaving it alone. Can we think about expressing that in another way that's a bit clearer, that's a bit more mathematical, that's completely unambiguous and can be understood by anybody who just comes along and says, what are we talking about here? Let's look at these next two. So start with a number, so 23, and add 0 to it. And the answer is the starting number. Okay, that seems to make sense. It's kind of a mathematical way of thinking. It's almost like following the number sentence. And the number is the same number, add 0. So that's kind of going backwards and maybe over here. So the number is the same number, add 0. Or you could even say 23 is equal to 23, add 0. That's another way you could represent that. So both of those are reasonable generalizations. Using mathematical terminology, using that kind of mathematical thinking that's almost like a process. And lastly, I like to think of this one down the bottom is kind of the plain English language version. When you add 0 to a number, you get the number you started with. So you could slot in any number. You could have 7, you could have 99, add 0 to the number, and you still end up with that first number you started with. So these ones down the bottom are probably the better generalizations compared to these shorter ones up here, which are open to interpretation and are a little bit vague. So when you're writing your generalization today, it doesn't need to be super long or super complex, but think about if someone comes along and just read that, and they didn't even have access to the number sentence or the pattern, how could they understand that? How could they interpret that? And you want to make sure that it's nice and clear, that it's true, obviously, and that it's using that mathematical language. And finally, here are our main ideas from today's lesson. In maths, a generalization is a statement about the properties of numbers, number relationships, operations, and much more. So it could be about shapes, 3D objects, angles, whatever. There's so many different generalizations we can make in maths, but we need to make sure that when we're making them, they are true, they're clear, they're unambiguous. That means that somebody's not going to come along and misinterpret them or misunderstand them. And lastly, they use mathematical language. Generalizing is an important part of working and thinking mathematically. So we do, to be good mathematicians, that's what we do. We're constantly trying to make generalizations, but then we're also testing those as well to see, well, actually, are they true? And finally, the process of generalizing is looking for underlying patterns or common properties in mathematics. Okay, that's all of our lesson for today. I'll see you in lesson 4. Thanks very much. Okay, welcome to lesson 4 for year 6 maths for week 6. Today we're going to be talking about displaying function patterns using graphs. Now today's lesson is a nice and short one compared to the rest of the ones this week. I know they've gone a little bit long. Today we're looking at representing function patterns on a graph, and specifically you're going to be using a dot plot to represent a simple function pattern on a graph. We're going to talk about recognizing why a dot plot is the appropriate or the better type of graph or chart to represent a function pattern. And also, to do this successfully, you'll need to be able to read the X and Y axes on a graph. Let's go back to Tuesday's activity with the pool and the pool tiles. So we saw that as the size of the pool increased, the number of tiles we needed to go around it increased as well. Makes sense. But there was actually a pattern to it as well. So the pool was represented by the blue square, and each tile was represented by the yellow squares. So here we had a pool value of 1, and we needed 8 tiles to go around it. And so one way you could have represented this pattern, there are different ways of representing it, but one way you could say was, well, the pool size, so that's the pool value here of 1, multiplied by 2, so that gets these ones here, plus 6 gets the end pieces, and gives us 8. So that's our pattern. Today, what we're going to look at is representing that or displaying that on a graph. So we go to this bit here. Now you can see I've chosen a dot plot. And I like a dot plot graph for this particular way of representing a function pattern because it's nice and simple. It doesn't have any additional messy information on there. I can just see the pattern as it goes up here, nice and simple. Now, to read this, it's really important that I am able to distinguish between my x-axis, which is the horizontal axis down here, and the y-axis here. And you'll see I've circled the headings or labels for each of these axes. Now, when you're creating a graph of any kind, it's so important that you label your x and your y axis, because I could switch this around. I could have this bit down here as the number of tiles and this bit here as the pool size. Also on this graph, and it doesn't actually have this, is it needs to have a heading as well. Otherwise, someone will come across this graph in isolation by itself and they're not really too sure what it's representing, what it's about. What's this about the pool size and number of tiles? You'll see here that each of the intervals is evenly spaced out. Now I did this in Excel, so it's nice and simple. And for the y-axis, I actually have a line going across, a horizontal line, so it's nice and easy for my eye to see, okay, well, this is 8. I'm not sort of thinking, oh, is this 7? Particularly when you get further out here. You're like, is this 15? Or like my eye can't really track across. Well, I've got a nice line here to help me. And we can see with this pattern that it actually increases at a steady rate. Yep. So it goes up, add 2, add 2, add 2. That's we're using a recursive pattern to describe it. It goes up by 2. Now this is not the straightest line, but it would keep going like this all the way up in a straight line. And that's what we call a linear pattern. This is a linear function. It increases at a constant rate. So it's not kind of ducking and diving and weaving. It's going up as a straight line. Okay, so let's look at some different ways of representing this pattern on a graph. And I've chosen 3 different graphs. Now I said before that I prefer the dot plot because it doesn't have all this extraneous unnecessary information on it. And it's nice and easy to see how the pattern grows as a line. But let's also consider these 2 other types of graphs that we're fairly familiar with by now. And we'll be looking at these in more detail when we look at data in the coming weeks. So firstly, let's look at a pie chart. So we all know what a pie chart looks like. Here I've got a heading, growth pattern. It's not a particularly great heading, but it'll do for this purpose. And down the side here, I've got a key. And so it says 1, 2, 3, 4, 5, and 6. Now I'm assuming this means the size of the pool size. It doesn't actually even say, it should have a heading. And you can see here, and this is the 1 pool size, 2 pool size, and it's kind of gradually getting bigger. But think about whether it's really appropriate to represent this particular pattern on a pie chart, because we know with a pie chart that it represents a proportion of a whole. So this here would probably be about 1/5 or 20% of a whole. But with the pool, we can increase the size of the pool infinitely. It's not a part of some population or some whole. Each of the pools are individual, and we can increase the size infinitely. So it doesn't really make sense to display it on a pie chart. So I'd say it's completely inappropriate for this purpose, so I'm going to cross it out. Here we've got a bar chart. Again, I've got this heading, and this time it's a little bit better because I've got my axes, my y-axis is labeled number of tiles. And here down the bottom it's got term, which is really just the pool size. So I'm just going to put PS. And I can see here that I've got my discrete values. I've got the pool size of 1, and then it would get to, I think it's 8 is the first one. To make this better, I could probably label each of the bars. So it goes 8, and then what was it, times 2, so 4 plus 6 is 10, and so on. It keeps on going up by 2. Now, it's okay to represent it this way. It's actually quite a small chart. Apologies for that. You can sort of see a linear pattern here. But again, it's much easier to connect the dots, so to speak, on a dot plot than it is for a bar graph. There might be slight variations in the height of these. Also, I don't have the lines tracking across, so my eye can't see where they what the actual height, I suppose, of each of these bars is. In which case, it might be better to include a data label there, a number on the top of each of these, and you could do that on your dot plot as well. But for all intents and purposes, for today's activity, you're going to be doing a dot plot, and it really is the better way of representing this kind of pattern here. So that's it for today's lesson. I did say it would be a shorter one. The main ideas are dot plots are an effective and appropriate way to display a simple function pattern on a graph. If you're doing that, make sure you read the X and Y axes and their labels, and then you plot the dot on the appropriate coordinates. So here I've got some coordinates. Remembering I always put my X coordinate before my Y coordinate. So it'd be 1 and then 8, X coordinate of 2, and then Y coordinate of 10, so up to that. So joining those two together, and it's that simple. The rest of your activities today are more about identifying patterns and applying pattern rules. That's really the focus of this week, but I thought I should introduce you to this idea of plotting a pattern on a dot plot and showing how it's a linear pattern, that it grows, or increases, I should say, in a straight line. Now, there are other types of patterns that aren't linear. They might have a curve, or they might kind of go up and down, but we're not looking at those. We're just looking at this linear pattern today. All right, thank you very much, guys. Good luck, and I'll see you next week.